Hi all, welcome back. Alright, so here are some classes and types that we've seen and a few more we're going to see today. The first type that we saw was bool, and it implements and, or, and not. So if the bool type implements these. So the num class implements plus, minus, multiplication and the absolute value. So any type in the num class has to implement those. In the integral class, you also implement all of num plus div and mod. So div and mod is the integer division, and this is for the remainder. There are two types in the integral class, which are fixed precision integers and infinite precision integers. So arbitrary precision integers. Okay, and then also under num is this fractional type that implements slash division. So this is the one that returns a fractional number. Underneath fractional is floating that implements log, sine, exponent and their mathematical functions. And one type that's in here is double. So double is a floating. There are other types you could define. So for example, the rational numbers might be fractional but not floating. Then there's the EQ class, which implements equality and not equality. And underneath the EQ class is the ORD class, which implements greater than or equal to, less than or equal to, and less than. Okay. What we're going to look at today is three more types, namely lists, characters, and strings. And it turns out that string is pretty trivial because a string is just a list of characters. So we don't even need to, we can just use that as an example. But first of all, what we're going to do is look at guards. So guards are just if-then-else structures used in the definition of functions. So this one we can define my max of x and y, and it's now the guard is this condition. So before we used multiple rules when we had sort of constants or other values here, but now we can use conditions. So we could use if x is bigger than x, y, you get x, and otherwise you get y. You don't need to use this because, as we saw before, we can define if in the language, but it's just sometimes a nice syntax to use, and it's just sometimes a nice syntax to use. So it evaluates the guards. The first one succeeding, the corresponding expression is returned, and otherwise here is just sort of a nice syntax, and it just evaluates to true. So otherwise it's just a variable interact with true. The reason we put it in is because it reads nicely. Okay, it's for human beings. So in the general case, we have the name, we have the formal arguments of x1 to xk, and we have all these conditions, all these so-called guards, g1 to gn. It evaluates the g1 and g2 in turn until the first one evaluates a true, let's call it g of I, and then it returns the value of the corresponding expression. Okay, so an exception is raised if none of the guards are true, so we really want to avoid that. And it's typical to have the last condition to be otherwise. And otherwise is just a variable with the value true. So that's a useful thing to do. Think about how we can implement max 3, for example. Okay. Haskell also has an if-then-else structure. So there's, the syntax is, it's useful to be able to read it. Sometimes an if-then-else is a useful structure to also use. Okay, we're just going to use guards. Just assume we've seen them, we're just going to use them. Just syntax. All right, the more interesting case is lists. So a list is an ordered sequence of elements of the same type. So a list of type T, where T is a type, so it's a list of some particular type, is either the empty list or is the form that's head of the tail and the rest of the list. And H has got to be of type T, and R is a list of type the list of type T. So they both have got to be the same. So it's only have lists of the same type. And colon is an input, is an infix function. So it's actually called a constructor. Okay, so it's actually sort of a special type of function, but it's a function. And a list has a special syntax. We're going to write down abbreviations. So when we write down a number like this, the list containing 7 is an abbreviation for 7. Sometimes we call this cons, the constructor for the empty list. So it's 7 followed by the empty list. The list 5, 7 is abbreviation for 5 followed by 7 followed by the empty list. And 3, 5, 7 is then 3 followed by 5 followed by 7. And this one here, colon associates to the right. So colon. So we can actually write this. 3, 5, 7 is the same as 3, 5, 7. It's just 3, 5, 7 is just this list notation on the left is just a nice syntax. Now both this equality and less than can be used with patterns on the left-hand side of equality. So it can define functions like the head of h colon t is h. So we can define the head, and we've given this pattern of ht, and this one here matches the head, matches h, and t matches the tail. And here we're just returning h. And the function called tail takes in a list and returns the tail. Notice that both of these are not defined for the empty list. In fact, I'll give an exception if you call them. Okay. So here's an interesting example. So my append L1, L2 returns a list containing of L1 followed by the list of elements L2. So it's a list containing the elements of L1 followed by the elements of L2. Okay. And we're also going to define it in terms of this input function. So for example, 5 pluses, we could define the list containing elements of L1 followed by the list containing L2. These are going to be exactly the same, it's just a different syntax. The built-in syntax is 2 pluses. The other thing we'll do is a string is a list of characters. We're going to do type string is a list of characters or a character. So here's an example of a list of characters. Here's a character A, comma, the characters B, and it's going to be written as the string AB. And 1, 2, 3 plus AB gives an error, and if you think of a pile time error, it's because the types don't match. You don't have it. And the standard prelude, which is defined when you load it, uses plus plus for append. So let's have a look at this. So here's an example of my append. So here's my append returns a list containing the elements of L1 followed by the list containing the elements of L2. And we're just going to go through the case analysis. The first case is that L1 is empty, in which case there's no elements of L1, so it's just L2. In the second case, the only other case for a list is it's going to be the form of a head H and a tail. H is the head of the list and T is the tail. And going to do this, and if you think about what the first element of the result is, the first element of the result has to be H. Okay? And the rest of the list is what happens when you append T to L2. Okay, so let's have a look at this. Let's load GHCI, and we'll load lists, as it says. Load lists. Okay, and now we're going to look at my append 1, 2, 3, 7, 8, 9, and it's going to give you 1, 2, 3, 7, 8, 9 as we'd expect. My append functional fun gives me functional. Okay, so it just works for lists. So in fact, so we could also do quote A colon fun. So this is a character quote, single quotes of the character, double quotes gives me a list, and it's going to just be a fun. Okay. If we look at the type of my append, it's going to take a list of type A and a list of type A. Notice this has to be the same type, and it's going to return a list of type A, and this is true for any A. Okay, so that's what's going to happen here. So the type of my append is this. The type of the colon function is going to take an element of type A and a list of type A, and it's going to return a list of type A. Okay, and it doesn't really matter in here what it does. So here's the same definition with an infix form. Okay, so it has exactly the same definition before. We're just doing this construction here for the first argument, and we can just work exactly the same thing as before. Okay, so that's all there is in lists. So the only thing that's special here is this use of this pattern matching. So we don't need, so given a new type, we don't need to define accesses for it. We can just use pattern matching, and that turns out to be very, very useful. Okay, in class we're going to play with lots of different examples of lists. We're going to play with lists for most of the class. All right, that's all. I'll see you in class. Thanks.